Hey guys, structural analysis meeting. We're gonna cook tonight. This is mainly gonna be all the stuff I learned last year, just trying to implement it into one pretty much study. And hopefully you guys can learn from it. So as you can see on my screen, this is Workbench. There's a range of studies here, CFD, harmonic studies, more stuff, um, thermal studies. The one we're concerned with is going to be the static structural study. That's mainly what we use last year to simulate the aft. So you could literally just, as I did before, click and drag it onto the screen. So pretty much the way this works is you grab whatever study you want, you drag it in here. You could reference multiple studies. So if you want to do like a static structural study and then, I don't know, like where is it? Yeah, structural optimization study, you could literally just drag it here. It'll reference the other study. So if you want to like combine something that you simulated before, maybe integrate it into a new study, you can do that here pretty easily. So yeah, that's pretty much how you want to set up your studies on Workbench. Um, and yeah, let's just get started, I guess. So I already have, so first of all, engineering data. This is where you select all the materials you want to use. So if you go to edit, it'll show a list of materials. If you click on engineering data sources, it'll have a range of libraries you can pick from. I, I this is the one I use for um, the aluminum alloy I used last year. I think it should be here. Yeah, yeah. Aluminum wrought 6061 T6. So if you want to add a material to your study, there's a little plus sign on the side. Click that. And then this window right there is your materials window. If you want to exit out, you just click X. So now I added my material. If you have different forms of materials, you can find all in that library. You can also add it throughout the study if you want to. This is just like a way to do it before you start your full study if you already know what material each part is. So moving on from there, the geometry tab. So pretty much you could either create new geometry from the built-in CAD software, which I don't recommend using. It's pretty bad, and I tried making a bar one time and it almost crashed. So do not use that. The import geometry tab is what you'd be using for all the studies you'd be doing. Because you'd pretty much just be importing step files from Fusion onto here. So I'm gonna pull up the example file I made. And then it hit me with a check mark, so it knows I have the geometry in. And then now I can go on to set up the study. So model is pretty much just to look at your geometry. It doesn't really help you in the study. So then you can, unless you want to make like changes to your geometry that would help you throughout your study, make it more accurate, more detailed by making the mesh more accurate. You could go here to change that, but we don't really use that, and it's a real pain to set up. So you can just go straight to setup. So if you double click setup, it'll open up mechanical, which is a, one of the applications Ansys has for structure simulations. There's different applications, I guess. There's Fluent for computational fluid dynamics, which you could use. But that is not what we're doing today. So static structural. I don't know why this is taking so long. Please don't crash. Let's go. Okay. Um, yeah, so this is the assembly I already had. It literally just
We only
imports it
see the
into here.
workbench right now.
No, wait, hold on. Um, you see it?
No.
Do you see it now?
Yes.
Let's go. Okay. So pretty much once it opens up mechanical, it's going to open it in a new window. And then your geometry is literally going to get imported into that new window. And this is where you're going to set up your study. So you can see a number of different tabs here: geometry imports, geometry materials, coordinate system connection mesh, etc. So you want to start off with your geometry. And this is where you're going to put all your material selections. So if you go to this component, for example, um, you can see down here. Let me, the way you access details related to a certain part is you go to the home screen, go to manage, and then there's a details option. You can also, there's a shortcut for it, it's Control D. If you press that, it'll show you all the details for pretty much anything you select. Ranges from meshes to parts to material selection to forces, anything. So that's the main tab you're going to use to, I guess, assign your inputs. So if you go here, this is the bracket I'm going to use for this study, and I want it to be made out of aluminum. So if you go to the bottom, there's this material tab down there. And under assignment, it says structural steel, but I already selected aluminum initially. So I can just select that and it'll convert it to aluminum. So I'm going to do the same for the other part. Oh, no. So yeah, if you click on materials, it'll pull up this weird window. If you exit out of it, it'll show you all the different materials by color. So you can just make sure that you have the right materials assigned to each part, because the last thing you want is to run a simulation, have it converge, have everything right, and then just have the wrong material selection, just get the wrong results as a consequence of that. So always be sure to assign the right materials to your parts. Yeah. So moving on, coordinate systems. The main goal, at least for me, for coordinate systems is during the mesh refinement process. So I'm going to talk about this further later, but just know that you can set up more than one coordinate system if you want to throughout a study. If you right click on coordinate systems, you can insert either a coordinate system at center of mass or a normal one. You go here, you could either do it by yellow boxes or things you need to fill out. So whenever you have a yellow box, that's like a necessary input for whatever you're trying to put into the study. So if I go to geometry, I want to select maybe this face right there. It'll automatically put it in the middle of this face. You could define it by either that or global coordinates. So you could put XYZ coordinates and have your coordinate system transform based off of that. So this is too much. This is also probably too much. Yeah. Change the X somewhere here. I don't know why you really need this to be here, but you can use coordinates if you really want to further refine where you want your coordinate system to be if you're working on your mesh. So that's something you could do, or you could do it the other way by selecting faces. And I think it'll automatically put it in the middle, if I'm pretty sure. Yeah. So face selection only puts it in the middle, and then you can do it by manually using coordinates. So that's coordinate systems connections. So pretty much, I think most of the stuff you're going to be simulating this year is going to be based off of an assembly. So the way Ansys input recognizes the difference between part and a part is through something called contacts. That pretty much differentiates, it tells Ansys that this part is mated to the other part in your assembly. So without putting in contacts, Ansys can't really know that you have different parts. It'll think it's just one part throughout the entire assembly and simulate it as such. And that'll cause errors when you simulate because that's not the case with assemblies. So the way you put a contact is if you right click on it, it'll give you this table. If you go to insert, you can insert a manual contact region. And then you have two tabs here your contact and your target. The way I try to think about contact and target, because selection does matter. Like it matters if I select this face, for example, as my contact and this one is my target, it'll be different than if I select the opposite. So if I do this bottom bracket as my contact and the other as my target. The way you usually want to do it is if you have a fixed support, whatever part is most closely influenced to that support is going to be your contact, and whatever's going into that's going to be your target. So in this case, I want the bottom of this bracket to be fixed. So my contact is going to be this face right there. Undo, please. Oh wait, I forgot about that. Yeah. Usually with assemblies, it automatically assigns contacts. This is usually it usually messes up this in the process, especially with big assemblies. So you'd have contacts for faces that don't intersect like here. Like as you can see, the blue face isn't even touching the red face. So this contact's just gonna fail. Um, and the other thing with contacts is you can't have oh, it selected two faces. Yeah. You can't have two faces intersecting two faces. It has to be one face touching one face. So if you have um this face right there and this face right there, that's one contact. This face right there, this face right there is another one. And it has to be that way, otherwise it'll just give you errors. So one thing to remember with contacts, it's always one face to one face. Even with like a countersunk screw, for example, um, you can't just select like both the shank and the countersink. You have to do like each one separately, which is pretty tedious. But that's the only way to get a convergent study. So let me delete both of those. Yeah, so my contact's going to be this face on the bracket, and then my target's going to be this face on the handle. And the one thing to note, if you want to hide any bodies or if any bodies are in the way, you can go back to your geometry tab, right click on whatever part you want, and it'll show the hide body option. So you can select that if you have like, for example, the screw contact I want to do here. I can't access that shank, so I have to hide this bracket. You could do that the way I just told you, or you could select the piece right there. Oh, right click on it, hide body. And then you can do your contact that way. So the second one's going to be the face of this screw. And the outer face of this bracket. So there's that. It'll show you both faces right there. If you just want a clearer view of what your contact's going to look like. So yeah, these can get pretty intense. I know the study we had last year, I'd say had around 200 of these within one study. So definitely one thing to keep in track. Like, because when you get to have more contacts, it's harder to keep track of each one. And if one of them's missing, the entire study's going to fail. And it's just really hard to determine which contact would be missing if you just maintain this naming convention. So I recommend renaming some of these contacts to something you'd remember better. That's just like an organizational thing you could do when you get to your study. But for now, I'm just going to stick with the default because we don't have that many contacts to begin with. So I'm gonna move on and do the rest of them. So One thing I forgot to talk about is the type of contact. So there's different types of contacts. Bonded contact means two parts are stuck together, they can't move. It's the quickest contact to simulate because it just assumes that the two parts interfacing each other can't move, and that wouldn't influence any nonlinearities in your study. So that's the quickest one. I wouldn't say it's the most accurate one, but it's the most time or the least time consuming one. There's different ones, frictionless, which is from the name, frictionless contact. Rough is the contact can move, I believe. That might be frictional actually. The contact can move and then you can define your friction coefficient. And then if the stress is high enough, it'll move the contact between two faces. This is really time consuming. Um, it really adds time to your simulation, especially if you have um, a lot of parts in your simulation. So I'd recommend just sticking to bonded. If there's any joint in particular you want to actually try to simulate, I'd recommend doing that, but generally don't try to change the contact type for most of your contacts. Um, so yeah, I'm yeah, I'm gonna move on to all the different contacts. I know this is pretty time consuming, but no. Oh, and I think a shortcut to restore all the hidden bodies is Shift F9. So that's something to make quicker in your study, I guess. And then the tabs up top that you keep on watching me switch to is different selection types. So you can select a point, select an edge, select the face, and then select the entire body. So this is what I've been using to generally the two most common are face and body. Um, so yeah, that's something to keep in mind. Um, to do this other contact, which is pretty much going to be the end shank of the screw and then the bracket. So it's pretty tedious, but it's be done. Okay, I think that should be it. Yeah, let's go. Okay, that should be all the contacts. So now we can move on to mesh. So, okay, initially I'm just gonna set up the automatic mesh generator and see what it gives me. This tends to be pretty bad, but there's methods to further refine it. So yeah, yeah, as you can see, the mesh is pretty coarse. So in regions of like high stress concentration, you won't really be able to differentiate this like the stress regime from this end of the bracket to this one, purely because there's like three elements in that section. So it's going to be pretty hard for the program to be able to differentiate different stress concentrations at different points. So generally you want um, a more fine mesh, which pretty much means more elements in your mesh. Um, and then there's different types of elements. So the element type it used here, an element, by the way, is these tiny little shapes that form the overall mesh. Um, there's different element types. So this is called tetrahedral. It's generally the most, it works the best with complex geometry, but it's not the most accurate, purely because of its shape. So generally with your mesh, you really don't want any sharp edges within your simulation. You can check something called your mesh quality, which will tell you how good of an element each element in your mesh is. And then to do that, you can go to the mesh tab right there. And there's this metrics display option. If you click on metrics graph, element quality, it'll show you, yeah. Oh my God. It'll show you the different, the decimal point is pretty much how good the element quality is. So the closer you are to one, the better your mesh is in general, the more accurate results you're going to get. So as you can see here, there's very few. The number of elements is pretty much the that are close to one are pretty much way lower than the ones that are not. So again, it'll split your geometry. I probably should lower this. It'll split your geometry to show you which elements specifically are of that quality. So based off of that, you can work out what works, what doesn't, what needs to be refined, and go from there. So that's just like one way to look at your mesh. Now I can't clear this. It's crazy. Okay, I'm gonna move on. Hope this works itself out. So there's several ways to refine your mesh. The first one is if you go to the bottom tab here, it'll show the different properties of your mesh. And one of them is element size. So here, if I do zero point 0.1 inches, for example, it'll show you this like pink outline for the mesh. And that means that it's an old the mesh you had before is an old mesh. You need to update it. So if you right click on mesh, click update. I don't know if that did anything. I might have to go lower. Okay, yeah, this is really annoying. Okay, so as you can see here, you have way more elements in your mesh. That's generally a good thing, although it will increase your computational time. So that's something to keep aware of or to be aware of. And then you go to your mesh graph. You can see that before, I don't know if you noticed, but there are more elements in this region, which is the really bad region. And generally, if the elements within this region, it means it's going to give you faulty results. So generally try to keep your element quality within as close to one as possible. So you could probably refine it further. Yeah. So I'm going to show you a couple ways to optimize your mesh within specific regions. So there's something called a mesh method, and that is pretty much you can change the element type on a specific face, specific body, my bad. Um, And then if you go to method, it'll show you the different element types you have. So a sweep, pretty much if you have a rod or a fastener that you want to mesh within a specific element type, you could do that using the sweep function. So pretty much it'll take whatever that rod is, it'll sweep it kind of like it does in CAD, and then it'll generate a mesh based off of that. And then you can change what type of elements you want on that sweep. So that's one option. You can do hex dominant, so it's pretty much going to generate a hexahedral mesh. And a hexahedral mesh generally is a square mesh, so it's not as much triangles and it's more square like. And that's generally better for just getting more accurate results in general because a hexahedral element has more nodes than a tetrahedral one. So there's more points for the software to actually calculate your force result and so on, and that'll generate a more reliable result. Let's hope this doesn't crash. Oh my God. Yeah. So as you can see right here, before it was all triangles, now it's all squares. You can go to your mesh graph again. It'll show you the different element types and then the quality of each element type. So that's something you can use to get a gauge of what element type works best for this specific geometry that you have. If you have to change anything about it, if you have more elements of that specific type, um, in the lower region, you probably want to reconsider what element type you select. General rule of thumb with hexahedral meshes or elements is that you need less of them to achieve the same results that you would need with a tetrahedral one. So just something to keep note, tetrahedral generally works better with more complex geometry, but you need a lot more elements to capture the same results as a hexahedral mesh, for example. One other thing you could do is mesh sizing. So this will you can pretty much change the size of a specific mesh in an area based off of a face or a body that you select using this feature. So if I select this top face, for example, um, you can put the element size. So what I have it before, 0.005, so maybe 0.003, actually 0.003. And then update the mesh. Yeah, see the difference between element numbers here and here. So a lot more elements in the face I selected than others. So if you want to refine your mesh within a specific region, for example, you got those fillets down there, and those tend to be pretty useful when it comes to structural analysis because they tend to be bearing the most load. So if I wanted to further refine this mesh, I could probably use a mesh sizing. However, I don't think the method I'm using currently would work because I'm selecting a face. So there's another method to do that, and that would include something called a sphere of influence. So for that, you need to set up a coordinate system, which is something I talked about before. For that, I don't need this. Insert a new one. And then what a sphere of influence is going to do pretty much is it's going to take your coordinate system, it's going to draw a circle around it. And whatever that circle radius is touching, is going to add a mesh specific element size to that specific region of your mesh. So if I have coordinate system that I just set up, I can go do a mesh sizing. Um, so if you go to type, there's two options, either element size or sphere of influence. So sphere center is going to be your coordinate system that you just made. And then you can change your radius. So too big. it'll show your circle radius um, within the feature. And then here you could define what element size you want for that specific region. So say I want 0.00303. I want to break my computer. I already put it. So now if you go to update your mesh, I hope I didn't put it too low. Are we good? Oh, there you go. Okay. Yeah. So as you can see here, you kind of have that circular effect. Probably not the best idea to use with hexahedral meshes, purely because that's a square and you're messing with a circular pattern. So probably save a sphere of influence only to be used with a tetrahedral one. So there's that. Those are, I think, most of the mesh manipulation tools that you could use throughout your study that are useful, I would say. So pretty much making your mesh smaller, making it coarser in certain areas, changing the mesh type or the element type to fit your specific requirements. Um, and yeah, after that, you can always just go to your mesh quality. Probably don't have the best one right now because this is purely a demonstration. Um, but yeah, based off of that, you can optimize your mesh for the best results. So after that, you can move on to your actual study. So this is where you're going to define all your supports, your forces, um, and anything that's pretty much influencing your structure throughout the study. So there's a handful of different supports and forces you could put. Pressure, hydrostatic pressure, if you're doing pressure vessels, force, mortar force, bearing force, bolt pretension, which is also something we used last year, which pretty much simulates any tightening you have on your fasteners before subjecting your structure to loading. That was pretty helpful for determining what the consequences of us pre-tensioning those bolts on the aft section would be during launch. So that's definitely a good tool to have. Um, so I'm just going to select a simple force and I put it up top here. And then one thing to note is this is only software. This shouldn't be used as a crutch to figure out your load case. Your load case should pretty much be figured out from hand calculations, from drawing a free body diagram, all that. Literally just static sum mom. Go from there, figure out the loading should be done there. And then once you move here, all you're doing here is literally applying your load onto the structure and seeing what happens and optimizing it based off of that. So this shouldn't justify your loading case. Your loading case should already be figured out. This is merely a way to see the effects of your loading on your structure. Um, so yeah, now that that's out of the way, already selected what face I wanted to place it on. I just put it on the top face. You can select your force magnitude. I'm gonna go for 100 pounds. And then for your direction, pretty much you can select any line in this assembly that is parallel to the force, and it'll automatically direct it to that direction. So if I wanted to select this line, the force would be going along that line. If I select that way, it'll be going vertically. And then to switch the direction of your force, you can use the bottom two arrows here. So if I click that, force pointing down, click the other one, force pointing up. So for now, I'm just going to keep it pointing down. Um, yeah, so I have my force. Now I got to set up my supports. So I want my bottom face right there to be fixed. So fix support, and then you can assign your face here, click apply, and then it'll set up your support. There's different types of supports. So there's frictionless supports, And those are mainly used if you have a part in your assembly that you're not including in your simulation and you want to account the contact of any part that is within that part that doesn't exist. Generally, what you want to do is put a frictionless support on it. You can put a frictional one, but I also don't recommend it. Same reason with contacts. It produces nonlinearities in your studies, and then that will affect your computational time and possibly could affect your results if you do it wrong. So stick to frictionless. You could also do a displacement support. So if you kind of have a gauge of how much a part's going to move, if you apply a force on it, you can put a displacement support on it. So say I know this handle right there is going to move, say like 1 centimeter. If I apply a force on it, I can put a displacement support on it that goes as far as 1 centimeter. So once that load is applied, your stress concentration isn't going to start growing until you've hit that limit within your displacement support. So until 1 centimeter, it's going to think that nothing's wrong, structure's fine. It should be that way. Um, so that's one support to consider. So I think that's all I need in terms of what is actually going into my study. So now I can go to my solution. So this is where you select all the different types of solutions you want. You can get deformation, strain, stress, energy, volume. Did not mean to do that. And if you go to your toolbox here, you can and go to stress tool, you can get your safety factor gauge for your study. So if that's something you're concerned about, trying to minimize that safety factor within an assembly, that's definitely a gauge that's useful. Only problem with that is make sure you have the right material type assigned, because pretty much what a safety factor is the ratio of your max stress over the ultimate tensile strength of that material. So if you have the wrong material, it's going to spit out the wrong safety factor. So definitely be aware of the material you're using. If it's even a different alloy than what you want, that'll change its properties. So that's definitely something to keep in mind. Um, but for now, I'm going to do a von Mises strain and then a stress strain, or a strain result and a stress result. I don't know why I said that. And then if you hit solve, it should start solving your study. All right, study solved. Um, this is not up to scale, so structure's not failing. This is your true scale. You can change your scale up here. You can go for crazy scale if you want to look at the effect of your forces and just get a better idea of what they're doing. If you really wanted to. This is not what's happening in real life. This is the true scale. So yeah, let me check if there's any inconsistencies within the results. So generally with your results, you don't want any sudden color spikes. So you want it to be gradual. That means there's enough elements in your region to um, take a gradual stress, um, implement a gradual stress regime within that section. So if there's any spikes within that regime, that just means that your mesh isn't up to standards with what it could be. And then obviously your results are not going to be as accurate as they should be. So it doesn't look like there's a lot of that here. The mesh could honestly be further refined. Yeah, you can kind of see it here. Just goes from blue to green, then like two squares. So yeah, definitely mesh could be further optimized. Um, Curious if this happens here. Yeah, you can generally see it if you have a coarse enough mesh. So generally go for a finer mesh. I think I went a little coarse with this one. Probably could be a little bit finer, but yeah, that's generally everything I think is useful in terms of setting up a static study. Um, are there any questions?
When you're preparing your mesh, is there a way to delete features that you don't need? I'm looking at like the fillets on that base part.
Like delete the feature that you don't have it like at all.
I'm looking at the like external fillets, the ones at the corners of that part.
Oh, yeah.
Yeah. Like those ones wouldn't really contribute at all to the like strength of the part. Is there a method to delete those so that you don't have to like add complexity to your mesh for them?
There is. I think it's done through the CAD software that's built into Ansys. I think you
Mhm.
have to go there and then physically add material here and then go back to your study and then material is going to be added here and then you can solve it that way. But from the study directly, I don't think you can add material to your mesh. There's a specific design model or tab that you have to go to before you go to the study tab.
Okay.
So I'd say probably get it right from Fusion. Because the CAD software here is horrible. Like I wouldn't recommend using it. Yeah.
Mhm. Thank you.
Um, cool. Any other questions?
I remember last year you mentioned there was something you could do to kind of have it generate like an efficient shape for you if you wanted to like cut down on like mass of something.
Yes. Yeah. Let me share the other screen. Okay, can you see the workbench screen?
No.
No?
Yes.
Okay. Yeah, so that's gonna have to be done using a separate study. So I think it's called structural optimization. So if you go here, and then drag it based off your go click on your solution tab, it'll pretty much transfer the solution of your current study and implement it into your other study. So it's technically two studies. So then you have to reset this study as well, um, so that you can get whatever you want out of it. This is pretty much gonna take your results and then based off of either mass recommendations or mesh recommendations, it's gonna take off material as much as possible until it meets those recommendations. Not material or not mesh recommendations, structural recommendations. My bad. Um, that's pretty much what it's going to be doing. Anything else? Oh, I forgot to mention this. If you're using screws in the study, do not use threads. Ansys does not like threads. Um, if you use a thread, it's going to break the study pretty much. I also don't recommend focusing too much of your mesh on your screw, especially if you have a lot of them, because that's going to add a lot of computational time and it's not necessarily going to give you that the results that you want. So as far as screws go, I'd recommend doing hand calculations on them pretty much to figure out what the forces are on them or what the stresses are on them. There is another way that I heard from my manager, the way they do it, they do something with it on like as a separate study and it accounts for vibration in it. Um, do not know what that is yet. When I do find out, I'll let you guys know. But as far as screws concerned, Hancocks. Do not rely on Ansys for screws.
I have a quick question. For the sphere of influence, can you do different geometries rather than a sphere? I know it's called sphere of influence, but like,
I don't know. Let me try to see. Yeah, I'm not sure. I'd have to look it up. Because the only two options are element size and sphere of influence.
okay, yeah.
There's got to be some sort of way to do a square, though. But then at that point, you could just literally do a mesh sizing for that
Mhm,
edge if you want to do a square. I don't think
mhm,
a square of influence would help you that much in that regard. I don't know.
mhm.
Anything else?
Doesn't seem like it. Thank you, George. I'm gonna go ahead and stop the recording.
Go.